Thank you very much, Roberto. Everyone, thanks for allowing me to come back home. That was very much appreciated. If anything is not going to be clear, just ask. It's absolutely fine. You can interrupt me at any single time. I don't mind, actually. I would prefer in this way, because otherwise you might forget what you wanted to ask. So today I'm going to talk about what I do for a researcher, which is basically roughly 1 hour every 7 months. But apart from that, what I usually do is our extragalactic transient. I study supernovae. For all of you that don't know what supernovae is, I'm going to introduce to the meaning, the words, and the physics going beyond it. Where are we going in terms of science, the physics, and what is coming next, all in the next 35 hours. So brace yourself. I hope you don't have any plan. I hope you brought food. It's going to be a really long ride. So what are supernovae? Supernovae is an old Latin word that basically identifies stellar explosions. Any kind of stars which are a little bit more massive than our sun, it does explode at the end of their life. If it is less than our sun, if it is in a binary system and is what is usually defined as a compact object, will explode as a supernova. AKA, be safe, our planet is not going to explode, our sun is not going to explode as a supernova. Most likely, humanity will destroy our planet much earlier than the sun. So that's absolutely a given from my point of view. However, when you talk about supernovae, which basically means is a nova from Latin, means a new stars in the cosmos, super because it was much brighter than normal novae. There are two main channels in which you can explode a star. The first one, if it's a stars, is in the zero, what is usually defined as zero-age main sequence stars. So going back to your studies, is basically what is basically where is our sun nowadays. Rather than one solar mass, if it is at least 8 times the mass of our sun, it will eventually evolve, becoming a red supergiant or any kind of other supergiant, blue or yellow, and it will finally explode as a supernova event. However, if it is nothing like this, it's less than 8 solar masses, and is a single binary system, that will not explode as a supernova. So there is not going to be any explosion involved. However, if you are in a binary system, when you have one of the two stars is a white dwarf are paradigm of stabilities, are the most stable stars of the universe. If left alone, at the end of the universe, whatever is going to end the universe, the white dwarf will still be a white dwarf. Leave it alone, it's absolutely fantastic. However, give them a friends, they're going to be a little bit unstable, whatever the friends it is. If the friend is a red supergiant, they're very close nearby. The white dwarf is one of the 3 compact objects. The other 2 are the neutron stars and the black holes. Compact objects in astrophysics have a real strong gravitational potential, aka they're going to attract the mass of every companion, every star's object that is too close to them. So the stars, the material from the red supergiant will go to the white dwarf. At a certain point, the white dwarf will get more and more material, so it starts to become less and less stable, and eventually will explode as what is known as a thermonuclear supernova. The other one, it could also be if there are 2 white dwarfs, which have been one of the 2, they've been evolved, they were far away enough to evolve during their life, which will eventually become white dwarf. But when they become white dwarf, they have a very strong gravitational potential, so they get to attract each other. They will spiral each other, and they will finally clash, creating the new trigger for explosion. So 2 main physical channels of explosion. This is called core collapse because at the end of this evolution, the long-standing battle between gravity and nuclear pressure caused by the nuclear reaction inside the stars will be finally won by gravity because there are no more nucleus to produce. There is no more radiation to produce. The radiation pressure, which is going from the center to the edges, is going to basically be nullified in 1 second, and the gravity will finally be able to push toward the center, creating basically a collapse, and then you will see the same sound. You will have an explosion which will bounce back to the universe. These 2 methods are the only one to create heavy nuclei in the cosmos because they synthesize all elements which are heavier than iron elements. So a lot of these material has been created into the cosmos are just a production of supernova explosions. Our sun all the material we have on our planet is because of supernova explosion. 3 generations of stars is the beauty cycle of life. You need a stellar to explode to create a new stars with more and more metals in it, which will create even planetary system around it. There is no way to escape this. So, but I'm an astronomer, and I used to be a physicist, and now I'm a lowly astronomer. And as such, I work a lot with what is basically observational data and analytical data. So how do we recognize stellar explosion? The first things we usually do as astronomers, we take images in the night skies of these objects. We measure the luminosities, and because astronomers are the evil cousins of physicists, we measure them in magnitudes. We don't measure this in flux, we don't measure this in watt, we use magnitudes, which are a very archaic version of luminosities. If you're not astronomers, if you want to be scared, just think the magnitude is minus 2.5, the logarithmic in base 10 of the flux. The minus 2.5 is what actually puts all the students off. It's completely arbitrary measure, and it's also negative. So the negative is the value, the brightest is the object. It's absolutely counterintuitive for any normal human beings. But here we are, astronomers, as I said before. So we take the snapshot. It's something like you take your phone, you will go into the night sky, and we take several timestamps because they're explosions. So they're transient. Every single time in their life is unique, it's not reproducible. We see this, and based on the different luminosity and luminosity evolution, we can try to differentiate between core collapse and thermonuclear supernovae. The other things we do, we take spectroscopy. These are basically electromagnetic information of the supernova explosion. What it is, it's the same things of taking a picture, but rather than having a single filter with your camera, you take a prism, and you like a prism, you differentiate the lights for all the wavelengths. Basically, you get a higher resolution across the wavelength, and then there's again astronomer. We don't use nanometer, we use angstrom because it's much cooler and it's a completely different symbol. These are 4,000 or 400 nanometers. So this is the optical part of the electromagnetic spectrum. The resolution is much higher, so we can see the peak and through of all the elements. And based what we see in this electromagnetic spectrum are the chemical composition of the elements, which together with the luminosities of the object, it tells us what kind of core collapse supernova, what kind of supernova explosion it is. If it is core collapse or if it is thermonuclear. We have like a lot of supernova types. I'm going to show you now in one single moment. But basically, thermonuclear supernova just one. All the rest are core collapse supernova. And seeing the picture of before, that was kind of intuitive. These are all range of different core collapse supernova that can explode. But the thermonuclear supernova, you only need the white dwarf. So there is less diversity in that case. The important stuff in terms of physics is that, as I mentioned before, it creates heavy nuclei, and especially isotopes of the cobalt and the nickel, which are radioactive decay, radioactive elements, which will power the luminosity of these objects. The rule of thumb, if you need very low-level extraction like IKEA, your main direction, the brighter the supernova is, the more nickel is produced in the supernova explosion. The longer it's going to last in terms of time, so the bigger it is, the more of the material, the bigger was the star at the beginning. So more of the material is being expelled into the cosmos. Very straightforward. Two things that you need to know, very easy to see from the luminosity evolution. But how we do specifically, we have now a lot of system of telescopes around the world that actually observe the night sky every single night. A lot of times even more twice in the same position of the night sky. We have reference images taken 5 to 10 years before with similar telescope of similar camera, and we do spot the differences. We take one after each other and we say, okay, if we take one after each other, there is a new object, we're going to see there is a new stars over there. We keep taking the magnitude, and then we see these. This is actually the explosions, goes up, right, and then it goes down the climb by the radioactive decay. And then we say, okay, that sounds like a supernova because usually it needs to rise for more than 2 magnitudes to be differentiated by novae. Just so that you know, for those of you that are not astronomers, the difference between supernova and nova is very subtle. Nova are usually fainter of 5 magnitudes, so 10 to the 5 in terms of flux, but they come from white dwarfs. So the differences, novae are cataclysmic event, so they can be repeated. Supernovae are catastrophic event, one, and that's done. You cannot repeat it. The other things we do, then we found one of these with these surveys. There are a lot in the world. They're in Canary Island, US, Australia, South Africa. A lot of them, they also have work in the same night. So you basically have an observation every 12 hours in some part of the world where it's always going to be always night. So you can observe basically for 24 hours in a row with no stop. And then we take an electromagnetic spectrum, and then we load these in repositories with a lot of previous example, and we say, oh, look, these two, they look the same. The blue, the sign, it was our old supernova, and the black is the data we just took 2 minutes ago. Oh, they look identical. This supernova tell me the kind of type of supernova, if it was a core collapse or not, and how old is this kind of supernova. So it's basically it's really a matching game. And that's has been brought by the survey that I'm leading. Is a 5 years survey that is 2024, but actually we have been extended for a 6th year in 2025. And we basically got more than 120 nights in a 4-meter observatory in Chile. That's the entire survey has been worth 8.5 million pounds. And 270 scientists has been working on these projects in the last 6 years. This is what happens if you leave astronomers unchecked. So this is what we can define the taxonomy of all the stellar explosion. I told you before, there are just 2 physical channels, thermonuclear and core collapse. Thermonuclear and core collapse, and this is what we came up with. So we look at observables rather than physics, and we created these entire zoos of supernovae. The things I do are these one, which are still unknown if they are core collapse or something even more exotic. And here you actually see if supernova at times, they can be mimicking something which are not a normal supernova explosion, because stars lose mass. Stars have big amount of gas and plasma, but during their life cycle, we have seen it with our planet, we've seen like with the aurora every single time, the stars lose mass to winds. But a lot of stars, the more massive, they also lose mass due to instabilities in the external layers. So they release material much more. And think about it, another important information, 50% of our stars are in binary system. Because of the gravitational potential, the one star, even if they're not exploded as supernova, can force another star to lose material just because of this. A lot of these are usually called X-ray transients or X-ray not binaries. So these materials floats around your object, and then when the supernova explodes, you will have a supernova is basically a shock. Is a shock wave that will clash with another medium, creating further shocks, which will completely change the observables I showed you before. And this is basically what happened when you have supernova in terms of electromagnetic spectra. These are the same things I showed you before. We identified different kind. All of these are all core collapse supernovae, just different. They're based on what you see in the external layers, because that's the other very interesting things. When you have a supernova explosions, the optical depth, the density is very high. So what you can only see what is on the surface of this optical depth. And stars are like onion. Even when they collapse and they explode, they will retain this onion structure. And as stars, the lighter elements are always on the external parts of the shell. So you will see hydrogen, helium, carbon, nitrogen, oxygen, so on and so forth. Different stars might have lost the hydrogen, and we see only the helium, like this one. And others, they might have retained the hydrogen, and we see this one. The main difference when you see this kind of peak, the wings is different. This profile with blue shifter absorption and a centroid emission is called a Piscini. It tells you usually there is a material which is moving into the cosmos are roughly 10,000 kilometers per second. So these are extremely energetic explosions, very fast. One single supernova explosions are the same power input, the same energy, actually the same energy conversion in terms of luminosity of an entire galaxy. A galaxy at 10 to the 41, 10 to the 35, 10 to 10 to the 41 stars, one single star is exploding at the same luminosity of all those stars. And as such, the kinetic energy involved are very high. Nowadays, we see a lot of differences. We see standard supernovae that later on interact with material. When they interact with material, the electromagnetic spectrum will change, and you will see this kind of very peaky kind of profile. For you that have done spectroscopy or of interacting of materials, even in terms of nuclear material, this is electron scattering. That is what you see. It is the electron scattering wings of the material. So this is the standard supernova scenario. 35, more than basically started with 87A a long time ago, but already Zwicky and Bade work on it in the 50s. So it's still very messy. I would say we have finally understood something, possibly, but this is what nowadays is our current scenario in terms of researcher on supernova science. So if you take the rise time scale, so when the stars explodes, it goes to the peak of the explosion and then goes decline. So from the explosion to the peak, that is what is in the x-axis, the rise time. And here is again the evil magnitude part of the astronomers versus the still evil part of the astronomers in luminosity, not in watts, but in ergs over seconds, because astronomers use CGS rather than SI measures, because why not? So we can mess up with all the other physicists, and it makes much happier, and we feel even smarter to understand what we're saying. If you see over this, a supernova explosion is very easy to understand. Higher nucleosynthesis, the nickel I said you before, the brighter is going to be in this plot. More mass, so the bigger is the explosions, the more we're going towards this direction. And then there are a lot of other things. Energy will pass to this one. If there is more opacity in the material, we're going down there, etc., etc. If we take our own distribution, this is what we observe in 40 years of core collapse and type 1a supernovae. If you take all the theories, like someone in the audience and someone else in the audience, the theoretical limit for supernova explosions are these two lines in this plot. So the solid is for thermonuclear, you would have guessed it, otherwise theory would have had to explain all of this, and this is for core collapse supernovae. However, 15 years ago, we started to find these two populations. The superluminous supernovae, there is not much fantasy over there. We call superluminous because guess what? They're brighter than normal supernovae. And F-bots because every good astronomer really is into acronyms. We strive into acronyms. And F-bots stands for fast blue optical transients. Fast, as you can see, they rise in much quicker than any core collapse. If you ever encountered the term kilonova, possibly after the gravitational wave discoveries in 2017, the kilonova stands here. It's very faint, very quick, less than 2 days to rise, but very faint. This is what tells us physics they can do. And then there is the matter of interaction, and I said you before, and this is basically what interaction can do. You can basically mimic everything except this one. This one, we really cannot do it. There is no way physics can do that to interaction. We tried, a lot of people tried, that is not possible. But all the rest, interaction between material exploded supernova and something was surrounding them, it can replicate a lot of these things. But it is truly interaction, or all these truly interaction? Maybe not. This gives you another idea of how supernovae are brighter than normal supernovae. As I said, they're much brighter. Interesting things, we can see supernovae of this because they're very bright into the deep universe. We can actually probe the first galaxies that ever formed in the universe to these supernovae. We can actually open to the worlds of the epoch of realization. And all these superluminous supernovae, they usually happen in low metallicity environment. Remember what I told you before. Supernova explosion increases the metallicity of an environment. So you need a lot of star formation, you need a lot of supernova explosion to increase your metallicity. Our galaxy, the Milky Way, has certain metal content. Our two satellite galaxies, which are the smaller, the large Magellanic Clouds, because they're smaller and they have less of this star formation, they have less metal contents. So these supernovae, they are in metallicity contents which are even lower than the Magellanic Clouds. We've been observing them for now 15 years, and then we discovered that there are at least 3 different populations in terms of luminosity evolution. I'm not going to give you a lot of details of the year, which would be even too much for experts in the sector, but this is just to give you an idea how much we have now been observed. In 15 years, we discovered this 15 years ago. We now have 270 examples of superluminous supernovae for one single reason. We know what to look for. We wanted to understand these because we didn't know what they are. So as all good researcher does it, oh, there's something now I like it, I'm going to look for it. That's easy. They were there even before, but we didn't know how to look at it. And of course, technology with all the new telescopes help us to understand what they are or to find them. The same goes for fast transients, which the fast transients, we have now like 20 to 30. And this is the evolution in the luminosities over time. The only difference that I showed you before, that there is a lot of differences. And when you see a lot of difference in terms of luminosity, it's very hard to explain with one single explosion mechanism. The tricky things for this one is that because they are so fast, they're very, very hard, even if you have all these telescopes at disposal, to actually recognize them as true interesting objects and then taking a spectrum. Just to give you an idea, spectroscopy, which I showed you before, is basically the bottleneck of heavy extragalactic transient, because to get like the equivalent faintness of a supernova explosion or any extragalactic transient that you can get with 1 meter telescope of a certain luminosities, you need a 4-meter telescope to get an electromagnetic spectrum with the same quality. The deeper you go, the bigger has to be the telescope. The more competitive is going to be the time for, the more you have to justify, okay, why do we need a lot of time to only do supernovae rather than cosmology or planets or star formation? The best things we came up with to explain these supernovae were parent-study supernovae, which is a theoretical way of exploding supernovae, which at the end is a power-up version of a thermonuclear supernova, because the trigger at the beginning is just a couple pair production, and then there is a thermonuclear supernova. However, the decline of these objects, it was even slower than the one we observed. These ones are brighter and slower than normal supernovae, but not as slow as these theoretical ideas. So what we came up after observing a lot of them, with 2 possible scenarios: the famous CSM interaction, because it can do a lot of things, versus a magnetar. So for those of you that are not astronomers, a magnetar is the equivalent of, is the most magnetic object we have in the cosmos. They are neutron stars, very rapidly spinning with a big magnetic field. It's roughly 10 to the 14 up to 10 16 Gauss. Our magnetic field is 1 Gauss in our planet. It's 10 to the 14 to the 16. If you're familiar with Marvel Comics, this is Magneto for the stars in the universe. It's the same things. It can the only catch is that we only ever observe 23 magnetars all in our galaxies, because they're very faint. And they're all spun up. It basically means with the time they lost momentum and energy, spiraling, just spinning, and they are much slower with respect to the one we need to replicate all the observables of these superluminous supernovae. Nevertheless, there is some kind of connection. These are actually much stronger when you go in metal-free environment, because they've not lost a lot of material. So the star itself has conserved the momentum. It has basically frozen the entire magnetic field. It gets much shorter, and basically what you have conservation of the momentum, which will create a dynamo effect. Bruno. The magnetar is a star. It's a neutron stars. It's a more magnetic neutron stars. The magnetic field is the magnetic field of the star itself. All stars have magnetic fields. When you basically have the collapse of the stars, all your fields of the magnetic stars, they get much closer to each other. So you increase the magnetic field. It's frozen. And because you are even spinning, you create a dynamo effect, which boosted the and again, basically mathematically, you can increase by a factor up to the 10 to the 8, the magnetic field of the original star. And they have been observed. 22 have been real, but they are neutral stars. Equivalent to, so neutral stars are usually called in two ways. Neutral stars, pulsar and magnetar, same thing. Pulsar just rotates faster, magnetar has a stronger magnetic field. Physically the same things. So yes, sorry, please go ahead.
Metallicity, for example, and a pulsar?
No.
No. Okay.
They are all in the same. The problem is that because they're not that bright, we didn't explore. So low metallicity galaxies, they are far away because they're back in time into cosmos. So you do not see a magnetar or a pulsar that far away, unless the pulsar has an X-ray which has beamed towards you. In the case, you can observe it. But the metallicity is the same. Is it's roughly the same. And especially our magnetars are in our own galaxy, which by definition is metallicity 1 standard. So here you can actually see there is a huge variety for the fast transients. But the more interesting is all of these are between something very similar to superluminous supernovae with magnetars, but you also have neutral stars, neutral star mergers, or you have other kind of compact objects like black holes, up to the mergers of compact objects, which in principle should also provide with gravitational wave signature. Especially this part of the years, it would be the merger between a neutral star and a black hole that, if close enough, it does produce gravitational signature, which can be observed by LIGO and LIGO, and in principle even from Virgo when it works. That is actually very interesting because it can allow us to reply to one of the strong, very broad astrophysical about what is the aftermath of a compact star merger. We only know the two white dwarf, and we only know the two neutral stars which produce gravitational waves, but all the other combination is still unknown, and there are a lot of them. So what's next? And this is the last slides, and I think it should have been in time. I thought 15, 28 hours. You said
20 days, yeah.
Oh, that's even better. My ego would be absolutely pleased to talk here for 20 days. You're losing point with the last comment. So where we stand now? So as I said before, I'm currently leading this pan-European effort. So it's 270 scientists which have come together to observe these any kind of these supernovae, including superluminous supernovae, to try to understand better the physics. We are now being observed by 640 nights over 6 years. In this one, we also was one of the previous Nobel Prize for physics in 2011, which is Brian Smith. He's also been in Pesto Plus. There is an Italian endeavor, which is SOX. Possibly not the best of the acronyms because those are SOX in English, but stands for Sonovac Shooter, which is going to actually replace the same instrument we're using in Pesto, which will observe supernovae. There is, however, the two main powerhouses in the next 10 years is going to be Euclid. Euclid is not ideal for supernovae because it observes the infrared sky, but it observes the sky one single time in 5 years. As you can see, there are transients. Like we need multiple observation, but you can still see a lot of information in the near infrared. We will not have it. A good one is going to be LSST, also known as Legacy Survey for Space and Time, at the Vera Rubin Observatory. This is a 6-meter telescope which is going to observe the night sky every night for 10 years in a row. One single night of data is going to be 22 terabytes of data. So one of the biggest astronomy survey, which is the Sloan Digital Sky Service, ran for 7 years, and it reached 122 terabytes of data after roughly 7 to 10 years. this is going to surpass the previous largest service at day 4. Just to give you an idea. And this is why there are lots of now data scientist AI jobs in astronomy, because there is no possible that you can even if you enslave all the astronomers of the world, you will do LSST stuff for the next year. Still not doing. It's not possible. In this specific, I'm also one of the UK executive board for LSST, where the UK consortium in the US has been, before Trump, had a lot of money in LSST. After Trump, I don't know if they will ever see it. But the cadence of LSST is not ideal for any kind of supernova transit, but in terms of superluminous, you will get roughly 1,100 superluminous supernova in the next 10 years. So we will get there a factor of 5, 45,000 fast transit. And in terms of interacting supernovae, as you can see, that basically they can be almost everything, more than 1 million. So there is a lot in the future in terms of these. And of course, take with a glimpse of salt, it's very biased because I'm in all of these consortium, and there's the perks of being all around the world for these. But it is interesting. It is interesting because we get to know what are basically the footprints of the evolution of the cosmos from our different ways. And a lot of very far away galaxy, we cannot understand them, the star formation, but we have basically the final products, which are the supernovae. This is the only way to actually understand and get this kind of information from supernovae. And of course, supernovae also been using cosmology as well, because they're very dependent on the omega matter and omega lambda in a way that CMB it is not. And this is very useful to have 2 different probes at the same time. With this, I stop annoying you with clearly the most interesting things that you have to do in astronomy and for the entire physics. So I would be absolutely gutted if by the time you walk that door, you will not go to your colleagues or supervisor, say, I've been enlightened, I want to change fields. So thanks again.
Thank you very much, Dr. Inserra. If there are curiosities, questions from the audience, you are free to ask.
You can ask even in Italian, and I can reply in English
yes.
for the sake of everyone.